the rest of the lecture should be pretty relaxing as we just go through some matrix algebra and derivation. So let me start sharing my screen. So yeah, you should at least see this derivation once in your life, just to say that you witnessed it and you can vouch for it. So this is setting up the notation. You have a scalar quantities, vectors, and with a single line, and matrices with a double line. So here's some examples, all pretty straightforward. And then obviously the transpose of the vector and matrices, matrix multiplication, all familiar to you guys. This quantity results in a scalar, and in fact, in the kind of the math of portfolio construction, you'll see this pattern a lot of like a vector times a matrix times a vector, and being a scalar quantity. And then we have if M is a square matrix, then its determinant is not zero, it's invertible, and so you're able to take the inverse. So now we just have kind of what the inverse of a matrix is. Fine. Now I'm going to introduce some real notation. So W is a vector of weights, mu is a vector of excess returns, and for convenience, I use E as a vector of all ones. And this is what the VCV matrix looks like. And yeah, and then this is what like an element looks like. Then we have some expressing some of the quantities we'll work with in vector notation. So the budget constraint that in vector form has weights sum to 1. We have the portfolio excess return given by this product of two vectors, and then we have the portfolio volatility. And then we can actually write the VCV matrix in terms of a volatility matrix and a correlation matrix and a volatility matrix. So where these volatility matrices are really just vectors, but we just expand them out in the matrix and put the vector components along the diagonal. And so this is a nice property where the volatility matrix is easily invertible, and the correlation matrix is has all ones along the diagonal. And then if you want to get into the details of coming up with the inverse of the VCV matrix, you can actually just focus on coming up with the inverse of the correlation matrix. Okay, so then what we want to calculate is the minimum variance portfolio. And so here's the risk return space and actually excess return, excess risk. And here's like a cloud of assets. And then here's the portfolio efficient frontier where there is no risk-free asset. And as I mentioned before, the global minimum variance portfolio is the portfolio that's has the lowest possible volatility. And so really the optimization problem is now pretty intuitively obvious. It's to minimize the portfolio volatility. Yeah, and you can see that the assets lie under the curve, because obviously if you had an asset outside, then that asset would dominate in terms of like a single asset would dominate the minimum variance portfolio or any portfolio along the efficient frontier. So in other words, anything outside, you could have an asset having a higher higher return and lower volatility than an efficient portfolio. So obviously the assets have to lie underneath. Okay, so it's more convenient, instead of having to take the square root all the time, is to work with the square volatility, which is also the variance. And so then we're going to minimize the variance as opposed to the volatility. It's the same thing. And it's going to be subject to the budget constraint. So that's our optimization problem. We set this up as the standard way of like the Lagrange multiplier. And so this is our Lagrangian. And we start taking our derivatives. And and then setting it to 0. So we want to satisfy this and this. The derivative with respect to mu is trivial. You just get back the budget, but this one is more involved. So what we'll do is solve this one. So if I go back, there's because the variance covariance matrix is symmetric, you can be a little bit loose with this taking the not fully taking into account the order of these. So I can just treat it as uh, 2 times, like derivative of this is this 2 times the variance matrix times the weight vector. So that's what I've done here. So I take the derivative of this, which is obviously 2 w's, but then like order doesn't matter because symmetry, and then I get like a mu e term. So fine, set that equal to 0. So I set those equal. I rearrange, and so then I find that the weights for the minimum variance portfolio is proportional to the inverse of the variance covariance matrix times my vector of 1s. And then the next thing is, similarly, when we derive the weights for equal vol weighting, we can apply the budget constraint to figure out what this this mu is, or to get rid of this mu piece. So that's what I do here. And so this is the final expression. So this is the minimum variance portfolio without any additional constraints. So examples of other constraints would be like a long only constraint. So this is a totally unconstrained. In other words, you're allowed to go long and short, and you can see this is obviously satisfies the budget constraint, because if I multiply the left-hand side by the e vector, I just get like the e inverse e, and same as the denominator, and just collapses down to 1. So that's pretty obvious. Okay, so one thing that you should note about this equation is that it doesn't involve mu. Mu, not this mu, but mu, the vector of excess returns. And in fact, this is a very special portfolio because it's the only portfolio on the efficient frontier that has that property. And which also makes it another nice property, because what that means is that you don't have to estimate returns to calculate the minimum variance portfolio. So that's another very nice and practical property. Yeah, and then I talk a little bit about the invertibility of the variance covariance matrix, and that means that you have to have positive eigenvalues. But from a financial term, it means that you need to have assets that are relatively uncorrelated to be able to invert the matrix. And so I just build up that intuition a little bit here and show that if you have uncorrelated assets, then the inversion is like a trivial and robust process. In other words, there'll be no issues with inversion. And then as you get more and more correlated, it gets harder and harder mathematically to be able to invert that matrix. And so there's tricks you can do to deal with that. So this is showing the inverse of the variance covariance matrix whenever all the assets are uncorrelated. So it's pretty trivial. And the intuition, and this is one of the things, like you might have noticed a theme in this lecture, that I'm not a big fan of mean variance optimization for portfolio construction or asset management. And so obviously you can do lots of things to help the mean variance to give sensible answers. And this is one of the things that you can do. So if you just naively dump in all your assets and data into the mean variance optimization, if you give it two assets that are very similar, so if you have assets A and B, whereas A has maybe just like a slightly higher return and a slightly lower volatility than B. So from a business point of view, both A and B are essentially the same. So from a business point of view, you'd say, well, I want to diversify as much as possible. So I want half of A and half of B, and that would create like you could think of that as like a synthetic position. And so if you wanted to help the optimizer, that's what you do. You combine A and B together into like a single security. Whereas if you don't do that, what's going to happen is the optimizer is going to say, oh, A is very correlated to B, but it's slightly better. So what I'm going to do is I'm going to put in essentially a very low risk position by going long A and short B, and to take advantage of the slight difference in excess return for A versus B. But you know that's not a meaningful difference. That's just noise. And so there's an example where the mean variance optimization gets tricked. So yeah, so this is where I say how you can address that problem. You can package up highly correlated assets and to give the optimizer a simpler job. Okay, so now we turn to the last topic, which is coming up with the weights for the mean variance, sorry, the maximum Sharpe ratio portfolio. Again, this is by now our old and bestest friend. And you know that the answer is going to be more complex because you know that it's going to involve the returns, or the excess returns, to be more precise. So it's a similar picture here. I haven't drawn it very well because it's clear like it's not the tangent portfolio, but you get the idea. It's some point along the efficient frontier. Okay, so now let's just set up the problem, and this is the Sharpe ratio of the portfolio in terms of vector notation, and so then we're just going to like go brute force and directly maximize the Sharpe ratio over all possible weighting choices, but still satisfying a budget constraint. So we use our same trick as setting up the Lagrange multiplier, and there's various algebra to go through here. So I don't bother with the trivial derivative, but rather the derivative with respect to the weights. So obviously there's the weight, sorry, the first piece of the derivative is the taking the derivative with respect to the numerator part, that this gives this term here. And then more complicated is dealing with the denominator. So it's 1/2, and then knock down the -1/2 by another unit. So you get -3/2. And then you take the derivative of what's inside. And again, because of symmetry, we can simplify it to 2 times volatility times the weights. Then you gotta remember you still have the numerator piece. You take the derivative from the extra like mu piece here, or sorry, nu piece here, and you set that whole thing to 0, vector 0. So fine, we do a little bit of algebra. So we multiply through by weights on both sides, and you get this expression. And the only way that this holds true is if mu equals to 0, because these two terms cancel out. So fine. So now we go back to our Lagrangian, but now that we know this piece is 0, so now we're just left that we can just directly take the derivative of this, but that's lucky that we've actually already done that. So it's essentially a little bit of a repeat. And here's what we're setting to 0. We multiply through by the square root of the volatility, essentially the weight times VCV times the weight, and you're left with this expression here. So in other words, what this is saying is the excess return multiplied by some scalar is the is equal to the weight times this scalar. And so then what you can do is you can isolate out the weight. Oh, sorry. I'm skipping ahead too far. So yeah, so sorry. The next step is to multiply by the VCV matrix. So let me go back and see. Yeah, so since this is a scalar, multiplying by the inverse just hits this piece here, or hits the excess return vector. And then you apply it over here, so you hit the weight vector, so that's what we should get here. Oh, sorry. So you can actually, yeah, you can also interpret this piece as a scalar. So so treat this as a scalar, and yeah, I made a mistake. Okay, so I made a mistake by telling you that this piece here is a scalar, and it's not. And the reason why it's not is because this is not. This is mu. It's not mu transposed. So that was a mistake on my part. But really, it's this piece here. It's the weight transposed times the excess return vector. That this piece here is a scalar. So whenever I multiply by the inverse of the VCV matrix, it passes through the scalar, hits this matrix, and essentially annihilates it. So then now I'm left with this expression here. And now I can do my trick. So I divide both sides by this scalar, and that gives me an expression for weight on the weight vector on the left-hand side, and then a bunch of stuff on the right-hand side. But we know that this is a scalar and this is a scalar, and then we have this collapses down to a vector. But we know when we apply our budget constraint that we can essentially get rid of all this stuff here. And so by doing that, we find that all this stuff here is equal to 1 divided by this term here. So then I substitute that in. And again, it's the structure of the formula is very similar to the formula, the weight formula for the minimum volatility portfolio. The only difference is that the mu, aka the excess return vector, is replaced by the vector of ones. So that's very nice. It's clearly normalized. In other words, satisfies the budget constraint. So that's also nice. So this is actually a very powerful result in that we've got like an analytic expression, albeit unconstrained in terms of weights being long or short, for both the minimum variance portfolio and maximum Sharpe ratio portfolio. And as I mentioned, 2 portfolios is enough to trace out the entire efficient frontier. Now we've got an analytic expression for the efficient frontier. So what you can start doing, again, what I show is given those linear combinations, you can start asking some questions. But yeah, so what I show is that mechanically how you can trace out the entire frontier. And so that means any portfolio along the efficient frontier is can start with the minimum variance portfolio, and then and then layered on top of it is like a long short portfolio off the maximum short ratio portfolio and the minimum variance portfolio. So this is actually a very elegant result. So you can think of this as some kind of risk aversion parameter, but you can imagine if this quantity is one, so if gamma is one, then I'm I'm at the minimum variance portfolio. So that would be gamma is one is your most is being risk adverse. And then you can imagine if gamma goes to infinity. Oh, sorry, I messed it up because it's backwards. So if gamma is one, then this and this cancel out, and I'm left with the maximum Sharpe ratio portfolio. So gamma equals to one gives me the maximum Sharpe ratio portfolio. If gamma goes to infinity, that's when I'm most risk adverse because this whole term cancels out and I'm left with the minimum variance portfolio. And so then the other case would be if gamma is less than one. Yeah, I'm thinking what happens in that case. Anyway, we don't have to worry about it. We covered the risk parameter range going from sitting at the maximum Sharpe ratio portfolio all the way to well, actually, we do know what happens if we go back to here. So if this is the minimum variance portfolio, let's say P1 is the maximum Sharpe ratio portfolio. So the gamma from infinity to one traces out over there, and then as it goes lower, it gets more over here. And so what you're actually doing, let's say you're at this green point. What that green point is telling you is that you actually shorted the minimum variance portfolio to buy more of the maximum Sharpe ratio portfolio. So that's since there's no risk-free asset, you use the minimum variance portfolio as effectively your source of borrowing. So you're shorting this portfolio and buying more of the maximum Sharpe ratio portfolio to extend you onto there. Yeah, I should have looked ahead because it's got all these answers instead of working it out in reply. Anyway, so yeah, so this is the complete equation for the efficient frontier, again with no risk-free asset. You can actually figure out what, you can play around some toy cases where you've got uncorrelated assets. The other thing that you can look at is you can ask the question, well, just let me check the time. Yeah, we're good. It's only 8:23. So just I'll wrap up in a couple more minutes. So there's this idea of the market portfolio, and the market portfolio contains essentially all available assets weighted by their size. But that portfolio is a long only portfolio. So in other words, it's not like the market portfolio has short like Microsoft or something like that. So then the question is, well, if the market portfolio is in some sense like an optimal portfolio, then shouldn't we find that the optimal portfolios that we've calculated along the efficient frontier, shouldn't we find that they're like where do we find like long only portfolios along that efficient frontier? So that's an interesting question to ask, and that's what we answer here. And so it turns out, like using this idea, it means that the weights, and we talked about this when we talked about the Yelp endowment model. We talked about how when you increase the risk or the volatility of the portfolio, so you move along the efficient frontier, what you're doing is you're decreasing the weight to the lower risky assets, even to a point where you actually get rid of them and perhaps even go short them. And this is showing that the weights are linear with the volatility. And so what that means is that you can imagine that the weight from some asset goes like this, and then the weight for another asset will go like that. And then during that region where they're both positive, that's a region where the portfolio, the optimal, the efficient frontier consists of only long-only portfolios. But then you can imagine adding more assets, and what happens is eventually the newer assets come in and cut through that region, making it smaller and smaller. So as you add more and more assets, the chance of finding a long-only portfolio becomes smaller and smaller. So there's some like technical results that you can show is that if there is a region if there is a region on the efficient frontier that's long only, there's only one region. And so there may be no region, but if there is a region, it's only like one section. And then the other thing that you can show is that the more assets you add, the narrower that region, if it exists, is going to be. And so that raises an interesting question: that how come the optimal portfolio can be have short assets in it, or efficient from portfolios can have short assets in it? Because if you think about it, like if the efficient portfolio is telling you, oh, you should be short this asset, well, then everybody should come to the same realization and therefore adjust the price of that asset so that it does become attractive, so that it is held in as a long only, like is held as a long position in the market portfolio. And so that's a little bit of a mystery of, or I shouldn't say mystery, but like an inconsistency between like the market portfolio and portfolios along the efficient frontier. And probably the reconciliation of that has to do with the mean variance, assuming that the inputs are so precise. And if you kind of add noise to the input assumptions, what you'll find is you tend to have more long only positions. So things start to make more sense. So it's kind of the generalization of that idea I had where you have like stock A and stock B that are highly correlated, and you go long A and long B. Long A and short B. So similarly, in like an optimization portfolio, you'll have lots of those examples. But as you kind of blend those in, so if you add some noise, you'll end up having 50% in A and 50% in B instead of like short one and long the other. And so that's the intuition behind the market portfolio being consisting of long only positions, whereas mean optimization oftentimes giving you solutions that have short positions. Okay, so that was everything I wanted to cover. So let me turn it over, unmute you guys. And if you guys have any questions, or otherwise we'll wrap up. Yeah, I believe your assignment is due on Tuesday. So, take some time to read it, and then just in case you have any questions, and I'll try to respond to you whenever you send anything. Oh, and by the way, yeah, this is the first assignment was the data focused assignment, and this assignment is a math focused assignment, and so it was useful that we went through this material because it's related. Okay, so enjoy your long weekend and see you on Monday. Thank you.